All right, Swedish Washroom. Welcome everybody to the Bin Podcast. I'm Mikey Famine. And the Bin Podcast, this is the first podcast to time travel. You would know that if you listened to the show that was on yesterday. This exact show happened yesterday.
I see what Mikey's doing.
See? Okay. You guys just weren't there for it. You know what I mean? Literally there. Had to be in that moment in the time stream.
Yeah.
We grabbed this moment and took it and brought it to yesterday, and now we're redoing. This is the repeat.
So if you're watching this now on YouTube,
time flux.
Oh, you missed out. You didn't get to live.
So they probably know what already happened.
Right.
Yep.
But they haven't seen it yet.
You have to tell us because it hasn't happened yet for us.
Yeah, so we're going to just look at the chat and wait for you guys to list off everything that happens in the show. And
everything we've done wrong in your real time because it's not our real time.
And if you've got the lottery numbers, speak up or forever hold your peace.
Yeah. And of course, it's all this space-time stuff where their arc is different than ours. So enjoy your space-time.
Those beautiful dulcet tones are one of Landon Curtnell, who has joined us again. Hello, Landon.
Good morning, good afternoon, or good evening, depending on your time zone and latitude and cosmic perspective. I am really pleased to be here. This particular show had been planned for a while.
Yes.
But the fact that we're doing the show is a good sign.
The last time you were here, we talked about space, and you broke my heart, and you told me that all this cool stuff was coming in like 5 months. Well, today's the day.
Yeah.
I've been biding my time.
And we said was, well, we're going to wait until we know it actually works. It would have been really a bummer to say, yeah, that would have been a nice scope. It works. It works. It works really well. So we're going to do some deep dive into the universe.
Yeah, Landon, your mouth wrote some checks that your fax just cashed.
Right, right. You sold me a bill of goods, and now you are delivering said goods.
Landon's just like this.
Yeah.
Have some sides. Have some sides. Have some sides.
So, I don't know what the introductions, or you want to just dive into space stuff? And of course, please, if people are on near our space-time curve, and you manage to get a message to us, get your question in, and we'll endeavor to engage.
And for everybody who's listening, after the fact on Monday morning, or you're on YouTube on Monday morning, this is why you got to check out the show live, because you could have got your questions answered, but you're not here. You're over here on the replay. Just call off work on Thursdays and come hang out with us.
Yeah, and we'll apologize ahead of time for the mistakes we make. But people with world lines in the future are so much more knowledgeable than we are.
And if the lovely police officers outside my house, Lily and Harvey, would like to ask a question, please.
Hi, Lily.
Do.
Hi, Harvey.
Hi, Lily.
Hi. I'll see you in a minute. Don't park in my space.
All right.
Yes.
Shall we share?
Yes, I'm ready for your share.
Okay. Let's do the start sharing thing. So, the Space Telescope worked, and this is an artist's conception here. I guess the main thing to consider is that this telescope is more than just a bigger Hubble. This telescope has a window on the universe that would have been impossible for the Hubble to do. The big thing is that there's a lot in the universe in frequencies that are, because of the way the universe is expanding, much longer, right? And in particular, people are surprised to say that this particular James Webb Telescope is not very good in the optical as we see. It is looking at things much longer wavelengths. So think about a piano. Our vision is just one octave on a piano, right? Of frequencies from red, the longest to violet. Right? That's what we can see. What the James Webb Telescope does is it goes 7 octaves down from where we can see. So imagine a song limited on just an octave. I know that some pop songs are like that, but versus having an entire piano that you can see, and this is what this is now. Now you say, well, why didn't they just put an infrared sensor on Hubble or something like that? What's the problem, or launch things? Well, the problem is that those frequencies down there, those base notes, are also the frequencies at which warm objects glow, right? Have you ever seen a thermal image? One of those sort of spy camera thermal images you can see of people.
I play a lot of video games, Landon. Of course, I know what a thermal scope is.
Yeah. So those are looking down in infrared. Now imagine that you're trying to see starlight down in those frequencies, and you got all this glowy stuff. It's like saying, like having a bunch of searchlights on an optical telescope and trying to see the heavens, right? It doesn't do it well. So what they had to do was they had to get away from Earth, right, where it's warm, glowy stuff. But the other thing as well is that even the telescope itself, if the telescope itself was even cold to things like even to that liquid nitrogen temperature, it's still glowing, and the telescope itself would just shine. It's like you don't want to use a light bulb as part of your telescope, right? That sort of thing. So they had to get this telescope out in space, away from the sun. So it can see these other images, and so this is what you're seeing, a picture of the Webb telescope with the hexagonal mirrors. That was done because they didn't have a big enough rocket to stick it in, and you're seeing this big thing down here at the bottom is this like tennis ball, as I say, tennis court sized heat shield, because the way it works out, if you go to the next set. The sun is down there glowing bright, and it's got basically this shade to keep the telescope cool. That's the thing, and the remarkable thing is that the telescope is actually cool in more ways than one. And in particular, if we look at right now what's happening with and let's make sure we're in the right units. So if you look at this thing, here's the telescope right now, and look at operating temperature, and let's just do civilized units because we don't need to do that Fahrenheit sillies. You see the hot side, cold side. Look at the hot side is 50 Celsius, halfway to boiling on the hot side, sun side, whereas the telescope itself is at minus 231. So from what we're saying is from this side over here, which would be halfway to boiling, down to here, much colder than liquid nitrogen. This is only 42 degrees above absolute zero on this side, right? Mm-hmm. So this telescope has to be that cold, because otherwise its thermal image would just outshine whatever it's looking at.
So the heat shield is basically taking away the interference that it would get from anything coming from the sun. Yes,
and you can't wait for nighttime, because that means you're behind the Earth and your Earth is glowing. So you really wanted to. So they had to put this way out and have this heat shield block and light block, so this monster telescope could stare out in space. Now it can't point towards the sun, right? It's got, because it will both blind and burn on the scope, but also would heat it up. So what you really have is that this is behind Earth. So think about sun, a line from sun to Earth to this Webb telescope. It's about 1 million kilometers beyond that sun-Earth line, and out in space, away from all the glowy Earth stuff. And it can basically have about half the sky. It can point around half the sky as long as you're looking away from the sun. Now, if you want to see something where the sun, near where the sun is, you just have to wait 6 months for it to turn around, and then it can see that sky. So it has half of the sky available to it when it looks at any one time.
So the turning radius of the James Webb is 1 year.
Yes, but while it's there, it has half the sky. But that's not a bad thing, because here on Earth, you've got this big ball. And sorry, flat Earthers, it's a ball.
Alleged ball.
This big ball that you can only see half the universe, right?
I thought it was a flat disc.
It's turtles all the way down.
You got it before I said it, Landon.
So this is part of the thing. Now you want to say, well, why? What's this whole thing about, besides having all these octaves of stuff? Why is it you want to see these longer wavelengths? Well, one of the reasons is that the universe is expanding, and some of those things early in the universe are so redshifted. They might have been glowy, even ultraviolet stuff, but by the time they get to us, they've been stretched to mid-infrared. Also, some of the things we want to look at are also colder than typical stars. If we want to look at planets aren't big glowy star things. They're at lower frequencies. If you want to look at some of the things that turned into a galaxy, you can't look at starlight. You look at colder stuff. So that's really why this thing was. It wanted to target things for which you can't see here on Earth, right? We can't build a giant infrared telescope on Earth, even above the atmosphere, even at the space station level, because the Earth is warm and glowy. So this is out in a unique spot that's never been seen before in any practical way. We've had space telescopes with liquid helium on it to give us a little glimpses of it while the helium boils away and then it's gone. This is a record, and it nearly.
Can you talk about the cooling system?
Yes. So several things. Here's a diagram with stuff. There are several cooling systems that it has. So what we're seeing here, if you can see my cursor, we have this is the mirror. So it's basically looking to the right. So starlight comes in from the right, bounces off of this hexagonal mirror, and it comes up to this little secondary mirror. The thing out in front is a mirror, and it bounces the light back through this little tube into the instrumentation system and gets sent down in the instruments. And there are kind of three kind of cooling systems going on here. First of all, there is a sunshade, right? And these tennis court-sized objects are basically mylar shields that reflect heat and keep light out. And in fact, you have about, if you're thinking in terms of sunscreen, this is like 1 billion SPF.
So
right?
Wayne, next time you're in Spain, get a couple of sun shields. Just a couple of sun shields, one for either shoulder.
Look at this scarring. Look at this scarring.
You look like Kratos.
Yes. Yeah, so those.
My shoulder looks like Thanos' chin.
See, if you've been running faster, those infrared photons would have been light stretched to infrared in you, but in a nice, warmy thing. But instead,
see, lazy.
You needed to be going at relative speed in order to stretch them out.
Landon, I was gonna ask a question on Mystery Hour today, but as I have you here, I'm gonna pick your brains. Why do I, as a brown Brit, only burn when I go to Spain?
Well, Spain actually, and of course, where it is, you're going to probably some of the drier parts of Spain.
Yeah, I went to the Canary Islands.
Yeah, and so one of the things there is that in fact that's a really good there's really good observatories there for a good reason. It's nice, clear, and dry, and in fact one of the things is you don't have that water vapor to absorb some of that ultraviolet light. You're getting stronger ultraviolet light than you normally would if you were sitting in, let's say, a London fog.
Okay.
If you really go there, come with me to the South Pole, where you're high up in the atmosphere and you're under the ozone hole. That's when you really can cook. But
what's the altitude down there? Because it's essentially like a mountaintop. The whole thing is like
Yes, it is. Antarctica is has the highest average above sea level ground of any continent, and even so you've got elevations that are between like 3,000 meters and 5,000 meters. So that's around, and those that are metrically challenged, it would be around 10,000 to maybe about 18,000 feet.
I feel it's
Can approach, right? 17 or it's going about 15,000 feet.
Does it have anything to do with the proximity to the equator in the sense of?
Yes, because it's even worse than even though the fact that that the Earth's spin causes the atmosphere. If you think like a giant pizza blob, right, spinning around, the atmosphere bulges out of the equator. So that's where you get thick tropical air and flattens the poles. So even though, like say, at the South Pole, you might be at 3,000 meters elevation, barometric pressure-wise, it's going to be about 5,000 meters. Right? So the air is very, 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 very thin. You're high altitude, it's dry, and you know that ozone hole that we've been talking about? That's where the ozone hole is. So you've got very strong, dry, high altitude, clear stuff, and you fry very well.
Them penguin farts are fucking potent, aren't they? Jesus.
Yeah. So back to the thing. So with a telescope, you have the shade, and you have these thermoelectric cooler, right? They're using electricity that are generated by essentially the solar panels. Solar panels are on the sun side of this thing. Has these electric coolers that go there. The easy way to do is you just put up a door of liquid helium, let the helium boil off, and you get really, really cold stuff. The problem is the helium runs out. So this thing electronically has a shade, has electric coolers to keep the instruments down to this cold temperature. And if you come back here and look at, this is a thing of where's Webb, you can see that the instruments are like, here's an instrument, even though on the shade side it's 42 Kelvin, minus 231 Celsius. This particular instrument is down at 6 Kelvin. This instrument is, as I say, it's almost 6 degrees Celsius colder, because this is the active electronic cooling. So it goes from halfway to boiling to near absolute zero to really close to absolute zero on this side. And again, because these are instruments that are going to look effectively at heat, taking pictures of heat, and you don't want the heater heating your you don't put a flash bulb inside your film camera.
So how do they regulate? Because obviously there are elements that need to stay cool and elements that need to have a degree of heat. So how have they balanced that out? Because obviously there are parts of the telescope that are on the cold side.
Yes, and so you see here these graphs, you can see the hot and cold side, through time. And so the things that are on the other side of the sunshade actually have solar panels because that's the way. This is a solar powered telescope, right? The thing you couldn't do, by the way, it is not perfectly in line with the Earth, right? There's a spot behind the Earth in the sun line that is really dark, but solar panels don't work there. So in fact, what it does, if you think about the line here, is the telescope kind of orbits a little bit outside the shadow. It goes around like this, and it's got this sort of weird orbit where if you're the sun and this is Earth, it's doing this sort of thing. It's coming around like this, right? Because it's got to be able to get out there and see. Hey, it's got to have solar panels,
right?
But it doesn't want the sunlight on the instrument. So that's where it's got this shade in front. So that's what's going on here. And you can see that there's part of the telescope that needs to keep warm. In fact, the solar panels, you want to be warm and catching sunlight, but other parts that are really, really cold.
So is it kind of using photovoltaic with like sunglasses?
Yes. So it's got, and the one side it's got solar panels, photovoltaic panels, and it's got these massive shades, and behind it is the telescope. taking the pictures,
Yeah.
sending the data through. And if you look at here, he's got these little, cute little antennas here. And so in the instruments, so the sunlight comes in from the right, bounces off the mirror, bounces off this mirror, comes inside here, goes bounce to an instrument that then detects the stuff and sends electrical signals out here to this little antenna that beams it to Earth.
All right.
Oh, wow.
I have a theory. No, I don't have a theory. I have a hypothesis. I always say that. I have to.
Everyone buckle up.
Yeah, buckle up. This is a good one. So, Landon, you've heard of that like weird paint stuff they have that's like that super darkest darkest black.
Yes.
That ultra.
Those are amazing stuff to look at.
It's really weird because you see a hole in a piece of paper, then you see the guy's finger touch the hole. I'm like, what the hell? It's very strange. Google it.
Yeah, I've stared at some of those things like the monoatomic layer of gold on a plate, which, by the way, gold doesn't get to be golden until it gets lumpy. Imagine, just a thin film of salt, and it isn't to the point where the salt becomes crystallized. You get the crystals. It's the lumpy gold that gives it its shine. When gold is deposited in a sort of almost like a monoatom layer or a couple atoms layer thick, it is very light absorptive, and when you look at a mirror like that, you expect to see you need to see something, but it's absorbing light. So you look at stuff and it looks like a hole. You're holding this thing and you can't see it, even though it's in front of you, because the light isn't bouncing off of it.
That's weird.
Right?
Oh,
and then you get a little dust particle there that lands on it, and then you can look at it and say, "Oh yeah, I think there's something there." Of course, if you touch it, then you ruin it. But
that's internal reflection, isn't it?
Yeah.
Yeah. So
it is weird to see that. That's how it's our experience. But
so can I use that super dark black paint on all my solar panels to absorb more light?
No.
You're not Landon.
Well,
let Landon tell me no.
I mean, part of the problem of doing that for absorbing more light is that one thing that solar panels have to do is also get the electricity coming out. You've got to get the photons to knock off electrons, but those electrons have to go someplace. Just taking electrons away from atoms doesn't do anything because they'll just come right back, right? You want the electrons to this is why it's like the photovoltaic stuff. The photon comes down and bangs into the surface of an atom, kicks off the electron, and you want the electron to say, "Go here. Here's a spot." And so if you look at those solar panels, you'll see a bunch of wires and what look like wires into it. And it also sometimes looks like they're all shattered, right? It looks like someone broke it. Well, those are really kind of getting the channels, the electrons that get bounced off of the surface, go to the conductors and conduct the electric field into the surface. That's how you get electric field out of it.
Yeah, but what if I ask nicely?
I'm sure. I'm sure you can ask nicely.
Landon, it's kind of like Mikey forgets what I do for a living.
I know, I just don't care.
So I wanted to also talk a little bit about, before we go into the image, because people are saying, where's the painting pictures, right? Another thing I wanted to talk about is you see with space telescopes or telescope stuff, you see these little spiky things, right? This is not a star with a punk hairdo. This is an artifact of what we call diffraction things. So the question is, well, what are these diffraction spikes? Why does it happen? Why is it that particular shape? Did they forget to focus it? No. This is physics, right? And so again, we see here's the main mirror where the photons come in, bounce off the secondary, and go into the instrument. And why does it happen? Well, it happens. Well, part of it happens because of the struts. I mean, the thing that is holding that secondary mirror there. You say, well, why didn't you interfere? Why didn't you put a camera out here? Well, the problem is you put a big camera out there. All that instrument package would sit in front of the camera, and you block your field of view, right? If all the instruments were sitting out here, well, first of all, then you'd have to shade it really well because it's colder back behind here, behind this shade. Remember, the sun is down there. So if you put all those instruments on this side, it would block your view. So we put it on the other side. Remember, again, the instrument package is down here where this is the electronics, the brains of the thing, the detectors are back here. We have to put it back here because if we put all that package out in front, it would block our field of view. So we have a secondary mirror out here that takes the light, bounces it again in through this stuff. This little cone here helps keep the stray light from coming into the instrument spot, right? We want only the light coming straight back to go to our instrument. So that means, but that thing can't just hover by itself. You need to have these little struts. And so these struts end up creating these patterns. The Hubble had 4 things. So you got sort of this 4-sided stuff. Here, the way it is, they have 6 because of the angles involved. And so also the mirror shape also has impact, right? If you just had a point source and you have a disk mirror, you get this sort of classic diffraction ring, right? You look at you get these sort of rings here.
Yeah.
If you had a square mirror, you would get something that looks like this. And a hexagonal mirror, you get something that looks like this. Has to do with the physics of the light waves. So in addition to the struts causing interference, you also have these things. And so the strut surface also has impact in terms of where it is. You get the how the bars help those patterns. So by the time you come up with the stuff, when you look at something, you'll get these spikes and these sort of fringes on it. But fortunately, this only happens. You only notice this for the brightest objects. But if you see these images, you say, well, why is that thing that weird? This is the physics of photons and the shape of the mirror and the struts and the things that hold together.
Well, that's different than what Brenna told me. Brenna told me it was unicorns.
Mm-hmm.
That is an explanation, but maybe not the one I would have come up with. So let's get to some cool image, right? Cartwheel Galaxy. This is the galaxy in a constellation Sculptor. It's about 500 million light years away, and this thing you can see down here. I can come in. Whoops, this thing. I can come in here to show. You can see that this thing that's talked about the distance of 100,000 light years. At the distance of this galaxy, that's spanning 100,000 light years. And we see it, this is called the Cartwright Galaxy because it looks like a cartwheel. The distance across here from side to side is 2.3 arc minutes. So what does that mean? Well, the full moon is about 30 arc minutes. So this is like 1/15 the angular size of what the moon looks like, full moon looks like up in the sky. And of course, that's side of. So we're seeing really, really tiny detail. And what's going on in this image? Well, the big thing of the show, we have essentially a case of a galaxy that had a collision. And I believe this collision occurred, we think, about 400 million years ago.
Wow.
And it has two rings. And there was a nice spiral galaxy here that hit for another galaxy over here. These things collided, and you can still see the effects of the spokes, but you also can see the impact. And there. Now, one of the things when the stars didn't run into each other, but the gas clouds did, and created a bunch of stuff where gas clouds slam together and create pockets of star formation. So this is what we call a starburst galaxy. And by the way, if you look about, we're talking about the diffraction spikes. Here's a fairly faint a star, which is, you see the diffraction spikes there, but the galaxy itself has a lot of detail. You can see down here the end of the spiral arm. So we have this ring here and that ring there, which are two galaxies that kind of pass through each other, and the gas clouds slam together. And so all these blue things here are really starbursts. There's a whole bunch of stars being born, little baby stars. going out there. Really baby solar systems going.
Baby
Land-
stars, do 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 do.
Don't. Oh, you.
Baby stars, do 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 do.
Landon.
Wayne has experienced that now.
Landon,
Yes.
if we ever meet in person, can you please not disclose to our eldest daughter that there is a Cartwheel Galaxy? Because all she will do is pester me to go there. Dad,
Yeah,
can we get
yeah.
to Cartwheel Galaxy? And I can do cartwheels. I can show him how to do a cartwheel.
But so some of the things as well you can see is that it took this, this particular image was taken on June 10th through 11th, right? And not only we see the details of stuff, but remember when I said blue, this isn't blue as in blue color. This particular image has near me. This is about 5 octaves of infrared compressed down into the visible, right? So we've transposed the frequencies because I can't show you infrared. I got to show you visual. So we transpose those frequencies up to visual. But hey, I got 5 octaves. I can only see 1 octave. So we're also compressing the stuff. So when you say blue, what we're really talking about is these were the shorter of the infrared, the heat, and the red is the longer stuff. Of course, in addition to that, when we zoom down here, we see a bunch of things. We can see galaxies. These are galaxies behind this galaxy that we never knew before because the dust of the galaxy would have hidden from it. And of course, we have these really, really faint things out here. You see, all these things are galaxies. All these little spots here are galaxies. Of course, look at this lovely little galaxy that we've never seen. We knew it was kind of there as it shows up in some of our telescopes as a fuzz, but this beautiful spiral galaxy that happens to be pointing towards us. Again, this thing here is about 100 billion stars, well-formed galaxy sitting behind this thing. This thing is only, this is only 500 million light years. So that means light left this 500 million years ago. And the universe size was such that it took 500 million years to get it. So this big thing here took 500 million years to get it. But these things that are farther, all these dots right here, these are all galaxies.
So basically,
galaxies.
Have they used to put in layman's term like a kind of Instagram filter to put it into a spectrum that we can actually see it?
Absolutely. Well, let's do that. Look at this. This is now because they say, okay, I saw the big composite image. Well, let's go to a filter, right? And so we're going to look at essentially now we're looking at the area which I believe this particular one is dealing with the mid-infrared. So these are some of the more base notes. We've taken out all those higher frequencies and we're looking just at the base notes. And notice the dramatic difference, right? From this thing here, let's unzoom it. From that thing there to here.
Wow.
Right? So we put in the filter, right? We put in the filter for just the very, very, very longest frequencies. And now we see the effect of the spiral arms here. We can see the 2 cartwheels. And notice, by the way, that galaxy that we saw. Let's come back. I'm sorry for folks. That galaxy.
Now, the Cartwheel Federation that own that galaxy have been building an armada for what Landon tells us is 500 million years, and they'll be hitting Earth this summer.
And notice, by the way, that other galaxy they have is gone because it doesn't have the infrared wavelengths to reach us that the other one does. But for example, and notice these 2 galaxies out here that are part of the collision. One is part of the collision, the other one's far behind. When you look at them in infrared, we see a very different thing. So for example,
I'm seeing Stargate.
And when you come in, like for example, these two things are galaxies. Right? These are galaxies. These are major galaxies that might have themselves 100 billion stars in them. When you look at it down in these frequencies, we now see that these are very, 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 even in the long wavelengths, they're very redshifted, very, very far back. And also we now see some of those galaxies that were barely peering through are now way behind. These are way, way, way behind. And we'll talk more about distant galaxies there. But again, we can get a lot more detail. Now, again, this is not a green galaxy. This is a wavelength that we have to transpose up into our octave of our limited eyesight. So you have to give it some color. So these are, you think of it as sort of false colors of stuff. But you can begin to see detail in things, like the fact that a blob up here, right? This sort of nondescript blob here. When you look at it at frequencies, we begin to see that it has a little bit of a spiral arm on it.
What is the exposure time for capturing these images?
I believe this particular exposure time was around 3 hours, if I recall correctly.
Wow.
Damn.
Right.
That's pretty sensitive equipment to do that for 3 hours.
And that's a pretty. We'll see some longer exposure stuff, but I wanted to show you again the rich data, right, that we get from these things, right? If you see these are representing. We can look at the physics and understand the materials involved, the speed, the distance, the compositions, because we've got this rich tapestry of frequencies to look at. And so it really is quite a special, a special thing just to be able to see this particular image. And what we're seeing here, so the blue stuff here in the cartwheel is dusty regions that are rich in hydrocarbons and other chemical compounds, like silicate dust. So you're seeing carbon and silicon stuff, right? I think you just look at a cosmic train wreck. It actually has created through those collisions and star bursts and so forth, and the stars go supernova and send out material that gets caught in the clouds. You're seeing hydrocarbons. You're seeing
pollution is what you're saying
of things that on Earth are important for life. So you might see these are the elements necessary for creating potential seeds for what might be life. We don't know there's life there, but this is an example of this nuclear synthesis that's creating these elements which here are very important for life. So just like a giant tree falls into the forest, crashes down, creates all kinds of destruction, knocks off stuff, but opens up the canopy, and all of a sudden these plants explode, the decay of the actual tree itself gets nutrients in the ground, and you have this whole ecosystem coming from on death of stuff. This cosmic train wreck has created literally billions of potential new stars. We're seeing, because it's a big galaxy, so billions of stars have switched on, and they're around those stars are seeded with elements like carbon and nitrogen and so forth, which can do interesting chemistry.
All right, I'm gonna jump in here for 1 second, Landon. I think, yep, there we go. If I can get the right screen here, we're gonna take a quick break, and we will see you guys for the second half of the show. So share with all your friends and get those questions ready for Landon.
Stay tuned, because there's some really cool images down below.
back, everybody. I hope you had a
Hello.
chance to grab a beverage, to use the facilities, to tell people that you love them.
Yes.
And we are back with the second half of the show with our very special, amazing guest, Landon, who is continuing to tell us more about what the James Webb Telescope has been giving us. It's a gift. It's a gift to us. So please continue. You have more images and more science-y stuff.
Yes. Well, thank you. And again, it really is a gift that we have. We're living in a time where this information is bringing to us, and I want to come to a more local neighborhood. And we were dealing with a Cartwheel Galaxy that was a 500 million light years away. We're going to come much closer. We're going to go back to about 7,600 light years away. In one of my favorite objects in the sky, the Karina Nebula. And Karina Nebula is in the southern hemisphere in the constellation Carina. And it has my favorite stars, Eta Carina. But if you're in the southern hemisphere, you would see this sizable nebula up in the line of the Milky Way that has some amazing images. And the James Webb Telescope focused on an edge of just a little portion of the Karina Nebula. So that's what we're seeing right now. Remember, we saw those star-forming regions. We see, look at all that it was showing up as blue. We talked about those hydrocarbon star-forming stuff. Well, we're going to look down at something that is more than 1,000 times closer to get more detail in one of these star-forming regions.
Go ahead, Wayne.
Right?
Landon, can you explain to us laymen and what we like to call thickos what a nebula is?
Thicko mode.
Nebula is just a big gas blob, right? There's a technical term, but a nebula basically it's like a fluffy cloud, but out in space. And the cloud is typically hydrogen, but it might have some helium, has some carbon, oxygen, and the usual sort of cast of elements out there. But basically, it's a pile of stuff. But that pile of stuff is very, very, very thin, right? Because the cloud you might see up in the sky, water cloud, is millions to billions of times more dense than these kind of clouds. No less, these are massive, right? These clouds are like the Karina Nebula has a mass several thousand times the mass of just our star. So they're a lot of mass, but they're big. But they form the seeds for forming stars and forming planetary systems, which is why us planetary scientists are really excited to look at these origins.
Brenna told me that those are unicorn farts.
That you could see cosmic uniform farts. That is an explanation, not mine.
Are we within a nebula? And the fact that we are within it, we can't see that we are.
Yeah, there is a nebula, though we're kind of in a little bubble that's been popped into the nebula, in part because radiation pressure, like our stars, has sort of pushed the gas out. But we can see the edges of the cocoon, which by the way, if we look towards the center of our galaxy, it's quite dark because there's clouds out there that block the starlight. So when you go to very, very dark skies and you see the Milky Way, the plane of our galaxy going overhead, if you look towards the center of our galaxy, you don't see it as well because there's this stuff in front of it. And visual light blocks it because it's absorbing light, and so you basically get a black spot. But if you look at the infrared, you can see through the galaxy, through those clouds, into the clouds, what's happening inside the clouds, what's behind it. And so this is a Karina Nebula, one of those. This is just a tiny edge of the nebula, again about 7 arc minutes across. So much smaller than the size of the moon up in the sky, angular size, and we're seeing a portion, and so you see this we they essentially call this sort of like the radiation, right? They've switched on. They're massive. They're hot. And in fact, up near there is Eta Carina, one of the most massive stars we know of in the universe, and it puts out all kinds of radiation. That radiation is hitting the gas cloud, and so think about you got this radiation wind that's striking what would have been just a nice fluffy thing minding its own business. It's now being blown back. So this is there's a wind, a stellar wind that's hitting the edge of this cloud, and that's part of why it's sort of lumpy. Is that it is. There's parts that are resisting the pressure. Like let's look down inside here. Let me focus on this stuff, and let's look inside this knot over here. And I'm going to zoom way in on that knot. Right? What's going on inside here? Well, you see, there's pressure that's coming in from above, but there's a lump here, and that lump means that this is a little lump or a knot that had the gravitational forces, the mass, to hold on to the material. And inside here we see this very faint thing. There's a star inside here, a couple other stars that are their own. They're holding on to the gas, resisting the pressure of the light that's going this way. And eventually this will break away, and this little cocoon will continue to collapse down and form a little solar system around some of these. In fact, several solar systems around some of these stars. So we're seeing a birth, like a birth sac of a baby solar system.
Does the color of the light determine what the star is made up of, and can we determine that by the color of?
Yes, we could, because we can see the chemical signatures, because certain elements have frequencies that resonate, and we can take carbon and oxygen and neon and so forth, put it into a laboratory, ionize it, and see the glow. The trick bit is that if this is redshifted, it's no longer neon green. Right. It might have been that or neon red or something like that. It might have been a neon color when it left, but it's been light stretched way down in the infrared if it's very far away.
So basically, we have to create the filter that it's going through to sort of like detangle it from what we're actually seeing. Yeah. So we create a filter, then we can say, right, it's definitely this because of, we've put all these different gases together, and we know that it's. Yeah. Okay. No, sorry. I'm being a bit completely layman here.
No, that's fine. So in addition to this thing, we can see. So this is a lump that's resisting the pressure. But we also see other stars being born. Like here's a star that's just been formed. It's switched on, and it is pushing the gas away from itself. So we're seeing the birth of a star here. Here's another inside here, this cocoon, and we've never seen it before. That little star there is the solar system that this gas cloud is holding on to, resisting the wind coming in from the top. Again, seeing birth of star systems. We have a bunch of material here. These stars that because whenever you compress gas, you get a lump. That lump has mass. It gravitationally pulls stuff together, and so you accelerate the formation of a star. And if it's got other heavy elements, you can accelerate the formation of planets. So all throughout this thing, again, look at the detail that we see down there. All throughout this stuff, we're seeing here's a lump here of a little solar system stars. Here's a star being switched on. Now these bright ones are in front of it. So those are night stars, but they're kind of photobombing the set. But this glow part here, inside here, are stars being formed. So this gas cloud is a nursery. Here's a couple of new stars that we've never seen before, whose actually it's condensed enough that we now see a fairly dense knot. Unlike that one thing over here that was fairly spaced out. These lumps over here have condensed to the point where you now actually have protoplanetary disks and planets in the process of being formed around these brand new stars. So we're seeing the birth of stuff. And again, if you saw this in visual light, there'd just be sort of this black shadow around it. But we can see into the shadow. We can see into the depths of stuff. We can see stars being formed and protoplanetary systems being formed. And the colors here, again, all redshifted, compressed to the 1 octave we can see, tell us about the chemistry involved, the chemicals, the elements that are involved. You can see these wisps, like you see these wisp arcs. There's a lump here, which as it pushes forward will turn into one of those little knots that'll hold on to stuff along. And deep inside here, we see other star-forming regions, which even something like the Hubble would not give us this. I mean, it's a gorgeous image in itself, but you're seeing the birth of mini stars and mini planetary systems, mini solar systems out in various stages of their evolving, right? So, sorry, back to here. Let's go back to the spot again. So you see also jets. It's like again, this lump here. This is a star that's switched on, and its pressure is creating jets of material to push stuff out. And we see very rich things. Now this region, this starburst region here, is a relatively short-lived phenomenon, right? As these stars pop on and blow bubbles, they're going to push more and more gas away, and what we left will be a cluster of stars with planets around them. This period lasts only about 50 to 100,000 years. Mm-hmm. So we went from just a lump of matter, very, very, very diffuse. And in fact, that matter was just minding its own business, seeing out there, just the atoms bouncing away, and then the shockwave hits it, bang. And what caused? Well, there's a big mass of stars up here whose pressure pushed against the gas cloud and began to collapse it. And that collapse created mass. That mass drew in more gas. So when you start creating a lump, that lump creates more lumps and stuff piles on. And so all throughout this stuff, and again, this is just a tiny section of it, 2 light years across at its distance here.
Now, Landon, in this tiny little snatch of an image, we can see stars that are like fairly close in proximity. Yep. But what is the actual distance relatively between these stars? I'm guessing it is light years, but it looks like,
well, if you look down here, this bar line down here, if you can see it, says 2 light years across, right? Mm-hmm. So that is essentially 20 trillion kilometers is that line.
Wow.
So these stars here might be 10 trillion kilometers across, if they're in the same plane. Now these bright stars in front, these are stars in front of it. So we have a couple of things that are sort of photobombing themselves, but if you look deeper in, so you see stars are actually inside the gas here. These are at the 7,600 light years away, and they're on the order of trillions of miles to tens of trillions of miles across. Now they may end up turning into a nice little cluster. This may turn into like the Pleiades, the 7 sisters,
my favorite constellation.
Right. This may eventually do it, but this period of starburst thing for the gas clouds collapsing only lasts for about 50 to 100,000 years, and it'll turn into a nice little open cluster of stars, we believe. But again, we're seeing the birth of solar systems, and those solar systems we can now tell from this infrared image that it's chemically rich. There's a chemical soup there, and you've got light and heat and so forth, and if those elements do the happy dance, you get little baby planets and who knows, maybe critters will grow up.
Would those stars that are relatively close together, would they kind of draw themselves into each other and create a,
but they could also scatter too, right? There's velocities involved in there, so they may also be scattering. we've seen the diameter of these open clusters tend to kind of scatter themselves out. And our star probably began in a nebula very similar to this. And it had a bunch of siblings. And one of the things that we're going to be looking for are where's the brothers and sisters of our sun? Now, we can look at the chemical elements that are in our planet system and say, well, you know, if the siblings of our sun are out there, and our sun created us, maybe they have the seeds of life where, if they're lucky, they could have stuff around there too.
Is it because we're so close to our star that we can't work out what ones would be the relatives? Where we look at a cluster in a gas cloud such as this, we can go, right, this one's with that one because we're so far away. But because we're so close up to the canvas, we can't see it.
Well, also the fact that it takes about 200 million years for us to go around our galaxy. And if our model of how our solar system is reasonably correct, we formed about 4.6 billion years ago. So that tells you we've had about 23, 24 spins around the wheel, and stuff is scattered and so forth. So it's been a little bit mixed up by this time. Remember that this birth region, this birth sac stuff of stars and a solar system happens only for a short period of time. But then eventually what happened, the other problem is that you say, well, there's a star. Well, okay, it's a star, but how do you know it's their sibling? Well, because you want to see the chemical signatures. Well, what are those chemical signatures? You need to see the light, the frequencies, those mid-infrared stuff to tell you what the chemicals are there to say, yes, they've got iron and nickel and you know, all those good things, phosphorus and nitrogen and so forth. You want to see that stuff to be able to say, yeah, and that star has a similar chemical soup to us. If you
I don't know.
These stars that come out of this. Go ahead.
I don't know. Sounds like spectroscopy, if you ask me.
Yes. Yeah. It's a pretty spectrally challenged stuff. But the spectroscopists are. So this might be a pretty picture, but what we do. Let's jump to the next set. Right. Next image. What we do is start looking at.
I just like the fact that Mikey learned a new word and crowbarred it in to make himself sound intelligent.
Yes. And to compliment Brenna. I bring it back in the second act.
So here's another thing for the set here. We're looking now a composite image in the mid-infrared. So we're doing one of those frequency slices. Same thing. And in fact, if you kind of look where we are, we're kind of that big lump. We saw that big knot we first saw is kind of up and to the left. So we're looking at a closer in image. And in particular, they were excited about, for example, this region here, right? Where we see, except for these blue ones here in front, there's a bunch of stars in here.
That's Dark Phoenix.
It looks like a giant. It looks like a giant eyeball from R-Type.
Yes, these are the baby stars.
That is the Watcher, guys.
And you see these little arcs here, right? This is the burst sac of those stars being thrown off, right? The pressure is pushing it out, and we're seeing the edges of that thing. So, so they're gonna go and stare at this spot. They didn't know the spot existed because in the visual stuff it just sees black wall, right? You see it, but here we know now there's a bunch of baby stars forming, and they've been stars for long enough that they pushed out their outer burst sac layers. And so we're going to then start looking at chemically detail what's going on near here. Because that's another thing is the James Webb Telescope is not a big giant survey. You're not going to do a big panel of stuff. We're talking about things. We were looking at things much smaller. I mean, this lump here, if you took a grain of salt and held it at arm's length, that grain of salt would be about 10 times bigger than this image. At arm's length. This is how tiny detail. This telescope's about looking at the fine details because the devil is in the detail, as they say, or the birth of the solar system is in the details.
I'm just really upset with you, Landon, that you put a space placenta on screen and didn't warn us at all.
Yeah, we're not going to talk about this spot here. Let's
Right,
move on.
no. Go back. Right now, all I'm thinking here is that was it Tangina from Dark Crystal, who talks about the Great Conjunction, the one who can pull her eye
Her
out.
name is Ogra.
Ogra.
Yeah.
Yeah.
That
Who
is
can
the
take-
Great Conjunction.
By the way, beyond this edge, you see these little things. There's galaxies out there. There's all these galaxies behind it, which we never knew before. They're sort of way in back.
How far away are some of those? What's like the furthest thing we've seen?
Well, we'll get to there. Let's go on. Let's go. Let's go. So let's move on.
Don't
let's move
spoil
on
it.
I can't help
So
myself.
as Mikey asked, and we will deliver. Let's move on to Stefan's quintet.
The furthest thing we've seen is Mikey's opinion.
Oh.
Oh, he's got a good opinion. So now.
Oh, you can't hear it, but it is played. But them's the breaks.
No.
You ain't got it.
But
Those of us in the northern hemisphere, this is in the constellation Pegasus, Stefan's quintet, and Stefan was the first person to see a pile of nebula. Right when we were called this nebulas, right? Just basically glowy stuff. Back in the early days, we didn't know these were galaxies. We just said, well, these were these glowing balls of gas. We didn't know what they were. And Stefan had a telescope where he found the first kind of thing of a curious cluster of things that are piled together. And in fact, there are 5. Now, what do you mean 5? 1, 2, 3, 4. There are 2 here. 5. Right? Now, it turns out that these, in terms of distance-wise, these 4 here are at around 290 million light years. So we're about half as close to that cartwheel. This happened to be in line, but at a different distance. So these 4 are locked into a dance. In fact, these 2 are spiraling into each other to merge.
They're married.
This one had an encounter of these 2 that's kind of bounced off, and you see this long trail of stars. Right? It kind of went by, and the thing sort of pulled it like taffy. And again, this is not gas. These are stars, right? These are stars being scattered around there as these things fling around. They'll eventually all merge into one happy galaxy, but for a while, it's pretty topsy-turvy in the mosh pit of Stefan's quintet.
They get rowdy up there.
Oh yeah, very rowdy.
Bumping into each other, but they'll help you
They
out.
got their like studded leather bracelets, their denim jackets.
Yeah.
What is the plural for nebula? Is it nebulae?
Yeah, I think so.
It's nebulas.
So the 5th one there, by the way, this 5th one is only about, this one is in front, only about, because these are 290 million light years. This one here is only about 40 million light years. So this happens to be in front, but not gravitationally bound to it. That's why it's not kind of stretched there. But there's something really interesting going on in this thing, right? If you dig down into here again, we're talking about, there's an incredible detail. Look at the dance of these 2 galaxies that are in the process of merging. And remember, talk about star forming regions. These are bursts of galaxies, bursts of stars and planetary systems going on there that we're going to look at in incredible detail, see these starburst regions. This one here has something really special going on. Now, you see, one of the things in particular do you see all these fuzzies? These are galaxies far behind that we never knew were there behind it, right? But there's a really bright, this is not a star in front. This is a region where it turns out there is a supermassive black hole.
Muse reference.
I'm surrounded by idiots.
And so let's look at more detail, because again, pretty pictures, but where is the science of it? Well, okay, one of the things you do is you can look at different slices, right? And so when you look at the slices, just like other things, like I tell you, we're seeing now one of the octaves being paired in. Now you can see the 2 distinct galaxies that were pretty almost merged together.
Wow.
You can see some of the bursts of material of again, But you see behind here, this is not a lump. This is a galaxy very far behind, way redshifted, right? It happens to be behind it. But if you go into here, now with this frequency, you can begin to see the spiral arms of that galaxy with something very active happening in the middle. Right? This guy's got some stuff going on in it. And of course, photobombing way behind it are these other galaxies going on. So let's look at in more detail. So we talk about the fact that we can look, this telescope can look at incredibly fine detail. So there's the galaxy that has this active supermassive black hole. And but we knew that something was going on there because we could see the radio emissions, right? It's just loud shouting radio stuff. Something is going on there. Now what's shouting? Not the black hole itself. That's light's not escaping. It's the gas that's swirling around inside it, and the spiral arm going down the drain. That spiral arm that spins and spins and spins, and then and bashes each other and gets stretched and skedified and so forth, and heats up to credible temperatures, right? So what we can do is the supermassive black hole. This is a zoomed in spot of that spot, which is zoomed in from even more so, right? We're looking at what does it look like near the black hole, and what does it look like a little bit farther out? And we can see a couple things. One of these, we can see things like molecular hydrogen. That's H2, two hydrogen atoms that have formed a chemical bond. We can go see silicates from star forming regions. Up here we see the same thing, but we also can see some more stuff of argon and neon and sulfur and other crazy elements going in there. But we can also tell that these spikes are spread out. Why? Because this thing is whipping around. You've got this thing spinning around right fast. So they've got an angular momentum that sort of skews the stuff. So we can tell the speed of the motion of the material going around this drain hole here, and we can see the temperatures of material. So we can tell about the temperatures and the velocities and the brightness, right, of stuff. Now, again, in terms of stuff, this is actually much brighter out here because it's kind of the edge of that whirlpool where stuff is whipping around pretty fast.
Like the photosphere?
Yes. And it has. So remember these galaxies...
Sorry, Landon. It's like Mikey's learnt a few new words this week, and he's just deploying them, willy and indeed nilly, trying to make himself look clever.
Well, he is kind of clever in various ways.
No, he's not.
Ha! In your face.
And so, by the way, if you look at, we're comparing the frequencies like here, right? And we can see, so this is the same frequency spectrum as this up here, where we're to the center versus the edge. And we could tell there's very different stuff going on here. Down here, we have silicates and molecular hydrogen near the center. But out here, spinning around, we can see more of the chemical soup. Now, why is chemical soup? Remember, these four galaxies have just had this dance where gas clouds are slamming each other and creating starburst regions and creating, and you get massive stars that go pop, 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 and they spew out their supernova materials.
It's Studio 54.
Yeah, so we see that material going on there. So we can look at this spot versus this spot and see very different characteristics, very different temperatures, very different velocities, all inside that spot here, which is just a bit of bright speck on a normal terrestrial telescope.
Sorry, dumb question again from the back.
Wayne, go ahead.
Prick. How do we determine these phenomena? Like, how do we determine that this is this particular element?
Yes. Well, we can in the laboratory take iron, turn to gas, struck electrons, turn into plasma, and have it glow like argon. We know what neon looks like. We know the relative frequencies. So the reason why we say this is argon, that's neon, and sulfur is we know the frequencies. Now the frequencies have been transposed, but they're all still similar to each other. The musical chord is there. It's just been transposed down to a different octave.
Okay. So, Mikey, not a stupid question, so fuck off.
Yes.
You said it. I just agreed with you.
So we're going to look at even that little central black hole spot and look at it in different wavelengths, right? So here coming back in, we're looking at the same spot, and we can identify saying, here's atomic hydrogen. What that means? That's just a proton sitting out there. It's lost an electron. It's just H. But here's iron. Here's some more atomic hydrogen. And why do we know it's atomic hydrogen? Because we know that those atoms resonate at a certain frequency, and we can see the musical notes. That helps us.
So what you determine in the lab is basically an elemental key that you then transpose onto what you see through the telescope, and then you can relate it to...
Exactly. And by the way, the transmission, how much you transposed has to do with how much redshift, it has to do with how far away it is and speeds. You get a lot of information just in the transposition. Look at this. So here we have atomic hydrogen, which is hot enough that they haven't come together, whereas this is molecular hydrogen, where it's cool enough that two hydrogen atoms have come together and form a bond of hydrogen gas as we know it here on Earth. And we can see these iron ions, right? This is iron, which is hot enough to ionize, because iron's got a nucleus with a lot of charge. It's going to keep on electrons. But if you hit it enough, it'll strip off the electrons. So we can see hot iron up here from some previous generation star, which exploded and sent out in supernova the iron stuff it created as it was in its death throes, that hit gas clouds and are forming. So we can see iron here, we can see molecular hydrogen, right? So it is we can look at these chemical compositions all from the fact that this one little tiny spot there gives us these different things. So when we see the color composite image, what we can break it down in individual sets and see phenomenon of chemistry and temperature and motion. All that's just one little pixel of this vast array of stuff. So we've been spending years pouring over this data, seeing stuff happening that we never knew was there before.
Can you go back to that last slide with the different colors real quick?
This one or this one?
Yeah. If you go down to the molecular hydrogen, yep. Is that the circle? Is that the hole? Is that the black hole?
I believe so. That the black hole's in that region. Now the part of the thing is, if you look at it in terms of size, is that the in order to be molecular hydrogen, it can't be too hot, because if it gets too hot, the hydrogen bond will break. Yeah. So this is a temperature where it hasn't gotten hot enough or ionized enough radiation from the stuff. The black hole itself isn't glowing, but the stuff falling into it reaches billions or trillions of degrees and radiates like crazy as it's spiraling down the drain hole. And that radiation can strip stuff off and create things. But there's other things here. This hydrogen ions. It's probably the case that inside here is one of those, like the Karina Nebula we saw, one of those lumps that are forming planetary systems inside here. This is where that could be the lump of a planetary system being formed. But unfortunately, it's being formed around this black hole region, and
they're gonna get very old very fast. I saw it in a documentary.
Yeah, I think so. So look at some stuff on the edge here as well. We can see, we can begin to take these things of known color stuff and look at argon versus neon versus molecular hydrogen, and get an idea about what's happening with the chemistry down there, which normally, if you just look at it optically, you just say shiny object.
Right.
But now we say it's more than just shiny object. It's got lots of stuff to teach us about the conditions that are going on inside this area. So I'd like to switch to a different image here, and this next one is called the Southern Ring Nebula. Now, this is what they call a planetary nebula. Bad name, because back in the days, people just saw these sort of round lumps and said they kind of look planetary. They're nebulas that kind of look planetary-like. If you squint, you say, okay, That's the planet. Well, imagine a bad telescope, but that name kind of stuck. So what's gone on here? Well, what we're seeing with this thing, this is around 2,000 light years away, so it's much closer than the Karina Nebula. And in this area, what we see is a star. There's a pair of stars, and this one star has blown off its outer layers. It's in the process. It's towards the end of its lifetime. It's shutting off its outer layer. This, by the way, is what's going to happen to our solar system.
No.
And our star. We'll get
I like our solar system.
Shut up.
What can we do to stop it?
Change physics.
Can we have a gig?
Can we start a GoFundMe to save our solar system?
So
save the solar system.
Can we get R.E.M. playing Homer Simpson's garage?
If you want my suggestion, is that we probably want to move neighborhoods by the time the sun goes there. It'd probably be an idea about find another star that's young and up and coming and stuff rather than
I see how it is.
Throw away the old sun. Get a
Landon has just mic dropped. We've got the Gen Z fucking star.
Yeah.
Fuck you, boomers.
Yes.
Yeah. So we have these are two pictures of the same thing. The one that's on the left is the near infrared, and this one over here, the one on the right is mid infrared, right? And so we're seeing different chemical compositions of the same thing. So one thing that happens with stars about the size of our mass of our sun is that they, towards the end of their lifetime, when they fuse up most of their hydrogen in their core, they no longer have the thermonuclear pressure to keep them glowing. So gravity begins to win and crush the star. And as the pressure and temperature inside the core, because of active pressure, goes up, all of a sudden those helium nuclei that the hydrogen was fusing together begin to smash into each other, right? They're able to overcome now, helium's got two positive charges, not just one. And you smash helium together and fuse it to create more things like neon and carbon and so forth. So when you saw those previous things, we were excited about neon, say, who cares about neon? Well, neon's one of those stages in stellar evolution, right? And here we're seeing, for stars like our sun, when they go to that next phase of fusing helium, much hotter, they expand, right? That the star gets really big, right? Because it blows up, because it's got more nuclear force pushing it out. And in fact, our star will expand to the point where its surface will be near the Earth orbit, right? About 6 billion years from now, we expect 6.5 billion years perhaps. Our sun will blow up to the point where the Earth might be just skimming the surface or under the surface of the sun. Bad spot here. So don't.
And that's when it becomes that's when it becomes a red giant. Yeah.
Yeah. Because that's the red giant phase.
Can we take the Earth with us?
Or the better parts of it. We can leave the parts we wrecked behind. Right?
Like Oklahoma, leave that.
All one of our listeners in Oklahoma are very upset.
Yeah. Well. So in this region, so what you see also is a time reference of the ejection from this white dwarf star. So the outer layers were ejected first, and then the inner layers. You're seeing shells. You're seeing shells blown off of the star, but because you're looking down on it, the edge of the shell appears thicker than the center. That's why it looks like a ring. This is basically the bubble. Looks like a soap bubble, but you have multiple bubbles inside each other expanding, where the inner one is most recently ejected, and then outer and outer and outer. So you're seeing a bunch of really interesting starbursts. Now, part of what this does, a part of this dance is it can be seen by this other the second one. So let's go into the first one here. This is just the infrared, right? And we see a bright star there. By the way, people saw this streak in even Hubble telescopes and thought this was like almost like a diffraction spike.
Yeah.
But it turns out that is actually a galaxy, edge on. We've learned now from the detail, we see there's a center core and there's spiral. It's flat. It has to be way behind here. And look, there's another galaxy we never knew a face on here. Behind this stuff, which we normally would have seen because we're seeing through the dust clouds behind as well. But we can see inside here the pressure from the star of the explosion and the inside edge of the bubble.
Mm.
Right? Think of it 3D. Think of this like you're seeing a 3D thing where you're seeing the backside and the edges.
It looks like almost like you're looking into like a cave.
Yes.
Yeah.
Like, and there's like a pool of water.
Yeah. I was gonna say, Landon, why? Well, you've got two very prominent stars in this particular picture.
Yeah.
There are peaks and troughs that seem to be inconsistent. You'd think it would be spherical.
Well, yes. I mean, but also the explosion from the star doesn't have to be circular. It might have had a big jet from the pole or the equator, a big sunspot burst that pushed it faster this way than that way. And by the way, this star here is happens to be just in front. This star they thought was kind of the originally early on they thought was kind of the cause of this bubble, but it turns out that there's another object in there. And in fact, we look in there. We look now into the mid-infrared, and we see what's happening. This is a binary star system.
That looks like a really sad face. Oh, I'm a star, am I? Oh, never mind.
Yeah, there's Marvin. Press robot. Your Hitchhiker's Guide to the Galaxy. So it turns out
42.
This star here, this cooler star, is the source of all this ring nebula. You have a binary pair. You've got a pair of stars. This is the white dwarf. This is his companion orbiting. And what's happening with the binary pair is that the white dwarf, the dense white core, is taking gas from the outer layers of his companion star and falling into this white dwarf. So the white dwarf has kind of a pylon of the outer layers of this other star piled on top of it. So when it had a lot of extra stuff to blow out when it did its giant puffy thing. Now it's down to this hot cinder of carbon. And even so, what will probably happen if this goes to the way it does is that gases from the outer layer of this star, when it goes into its phase, right? These are probably born at near the same time, so they're probably similar ages. Just like we saw with those Karina Nebulas, where you had a bunch of piles of stars. You know, well, what happens when the stars get close? Well, here's a pair that dance around each other. This one probably is just a little bit behind in age-wise of this one, but it'll go through its phase. It'll blow it up, but when it blows up, the material will pile on top of the white dwarf, and it'll get thicker and thicker and thicker to the point where all of a sudden the pressure of the hydrogen piling up on this white dwarf cylinder gets so intense that you get a bang. You get what's called a supernova, where you'll get a spectacular explosion that'll make this little ring puffs seem like a piker, right? This is going to go out.
I can't wait to see it, Landon. Don't tell me it's going to be a long time again.
Well, you might have to wait a while, but what you're looking at is what we see that this is a lit fuse with a pile of dynamite, and this stuff out here is just a little spark of the fuse going. The real bang is coming later.
How long later?
Tomorrow.
Well, it could be on the order of, I think on the order of tens of hundreds of millions of years, but it depends upon the age. In fact, one of the things we want to do is look at the chemical composition of this star versus that star. See, I'm
just gonna set a note in my phone.
Yeah, let me set a reminder on my calendar.
Before we could tell, if you look kind of carefully, you could see, well, there's a dot over there. And we thought, well, there's a couple of inconsequential dots, so why would we pay attention to that dot? Well, it turns out that dot is actually the cause of this of this thing. And when you go and look at the infrared, you can see they heat. Remember, this is the hotter thing. You can see the heat of the actual white dwarf that's causing this. And even though there might be the seeds of life, when this goes supernova, this is just going to go bang in a big way. It's bad for the cosmic neighborhood of here, but the stuff that sends out are going to hit some other gas cloud, which will make planets around that thing. So even though the seeds for life here are going to be destroyed, they're going to be scattered by the supernova, which is going to push it really fast, hit some other gas cloud, and form planets. And again, we can, before with visual stuff, you could barely detect that this other star existed. We knew it was a binary pair because we could see the star wobble, but we didn't know the details. Now with the James Webb, we can actually go point in and actually get an idea about what is the chemistry and the temperatures around nearby this star and this star, and we'll hope to see, you can see there's a little bit of, if you come in here, you can see what looks like a little bit of stuff coming off this star going this way. So we always see the beginning of the spiral stuff of the outer edge of this star that's puffed up, that's spiraling around, going around to this star. We can see the mass transfer occurring.
Can I just ask a question? Now, looking at the two distinct colours of those two stars, what are the main elements of those two stars that are in very close proximity?
I mean, the main elements are hydrogen and helium, but but we also will see carbon. Bring of the white dwarf, we'd see carbon, nitrogen, oxygen, and so it didn't get to the point. It isn't a massive star like at a Carina where it can go and produce iron and some of those other stuff. This is kind of in the mid-level areas. But when this thing, if this thing heads the way that it normally does and something else doesn't come along and disrupt it, when it goes supernova, it's going to generate the much more heavier elements, which will give you the nickels and the irons and then the cobalts and all that sort of good rich stuff.
So those two stars collapsing into each other, and inevitably.
No, but when this star here goes through its giant phase and blows up, it's got this gravitationally bound companion that's going to suck off the material and suck it down into its very dense stuff. Because again, the material inside this core of this white dwarf is ultra dense. I mean, this is like the thimblefuls worth of this white dwarf are millions of tons of material. Very dense, right? But when this thing blows up, it's not going to be able to do this nebula thing. Its stuff is going to pile on top of that thing, and the hydrogen is going to get deeper, 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 deeper. Because remember, the outside edge of the when the second one starts to fuse helium and blows up, its hydrogen shell is going to transfer over to the other one, pile up, hydrogen will get thicker and thicker and thicker, and all of a sudden it'll reach the pressure of thermonuclear explosion. You have a runaway explosion of almost indescribable power. Let's put it this way: when this outer layer is piled on top of here and it goes supernova, if you had a 1 megaton bomb right at the edge of your eye and you set it off and you're watching this 1 megaton bomb,
I've got one just here,
right? Versus being at the distance the star is from here, right? If you were over here watching this thermonuclear bomb, watching this thing go supernova, or you had a 1 megaton bomb right next to your eye when it goes off, the supernova will be 5 orders of magnitude, or 6, 1 million times brighter than a 1 megaton bomb right next to your eye.
Wow.
Even though you're at this distance, right? The power and so forth is tremendous. So even though this has got some nice elements being created, when this thing goes supernova, it's going to be able to send this stuff way out, create those shock waves. It'll hit some other gas cloud, but it'll hit a gas cloud with rich elements. So you get a bunch of iron and other important chemical stuff, which can cause a happy dance, hopefully.
I know a human lizard brain tries to make shapes out of everything. That just looks like a massive steak to me.
Yes. So I wanted to give you what is probably my most exciting image, but it doesn't look very pretty. This is a so
it's all
we're
right.
this isn't very pretty,
Yeah,
but oftentimes
cheer us up, why don't you?
oftentimes the things, the astronomy and science data is not pretty. I mean, it's data, and this is the one that this is just extraordinary amounts of information. What is this? This is a light curve. This is a spectral curve, right? We're seeing from 0.75 to 2.75. We're seeing about 3 octaves, and we're seeing the brightness of this is a brightness variation. These white dots are brightness variations, and it's light blocked. And what is it blocked? Well, there is a planet orbiting this star, and when it comes in front, it blocks a little bit of light.
Uh-oh.
Right? Now, this particular planet is about it's about I would say it orbits the star about every 3 days. So it takes about 3.5 days for this planet to orbit the star. It's really whipping around really close.
That boy
right?
is cooking.
But when it comes in front, the starlight drops a little bit. So we knew we could see the blink of the star changing 1% when the planet came in front. So we knew it was there. But the other thing about this planet is actually quite hot. It's close to the star. Right. This star is only about 1,150 light years away. So we're relatively close by. And it orbits very close to the star, about less than 1/20th distance of the sun. Like it's 20 times closer to its star than we are. Right. So it's really close in, high temperature set. It's a thing about mass about half the mass of Jupiter. So it's. Go ahead.
I'm glad you've gone down this angle, because I thought you and your fellow Pluto activist Brenner was about to start a protest on this channel, which we don't condone.
So yes, we want to avoid controversies. So size-wise, this is about 48% the mass of Jupiter. So a little less massive than Saturn, but a chunky planet. But so it's about 150 times the mass of Earth, but it's about 1.2 times the size of Jupiter. And the reason why is that it's very high temperature, so close to the star. It's 1,000 degrees. It is really high temperature. And so what's happening is when this star passes in front, when the planet passes in front of the star, right? It eclipses it for a period of time, and for about for about 2.5 hours is between this spot here where it begins to touch to this spot. You get 2.5 times where this is about a 2-hour time. Look at you see the time frame here.
Yeah.
And while it's in front, it blocks some light. And this shows you the amount of light blocked from the star in parts per million. And what's happening is the atmosphere is catching just Janus and photons from the star that are resonating with the stuff that's in this planet's atmosphere, are creating, are absorbing the light from behind it, and we can tell what's in the atmosphere of this planet. Even though this planet is 1,000 degrees, so it's vapor, we can see a chord, a musical chord, that's a major chord of water to hydrogen and oxygen. They're kind of charge bound, and they're vibrating away, high temperature, so they're really bouncing around, and it's resonating. We're seeing the tuning fork of water. So we saw water spike. This is stuff, and we know from the atmosphere, from water in the lab, that it resonates at these frequencies. But
Does this mean that you can determine whether there is viable life on this planet based on the calculations, the atmosphere, distance from sun?
Yes, because one of the things we're seeing, see these spikes out here, right? Now,
Yep.
we saw some of the first experiments, right? Kind of the rule for stuff is if you're the one that has got a couple hours of time on James Webb. These people had 6 hours and 23 minutes to look at every. They looked at three transits. So they had 280 brightness vary measurements once every 1.4 minutes for 6.5 hours to look at how the light changes when the planet was in front. And they looked at how the light from that star changed in parts per million. And they saw, first of all, these things say there's water vapor. Now, the rule is it's their telescope time, so you let them publish first. But they were nice to say, everyone wants to see what can the Hubble or the Webb do better than the Hubble. And so they said, I'll tell you what, we'll release our stuff, but be nice, don't publish stuff. Let us be the ones to publish. So they're going to publish papers, but you see the other spikes here? These other spikes?
Yeah.
There's some really interesting chemical soup. I can tell you that there's some nitrogen on there. There's some carbon. There's some, there's this other sort of things, little bits of sodium, potassium, some pretty interesting spikes here that are in the atmosphere. Think about this. This is a star which is about 11,000 trillion kilometers from Earth, with a hot multi-thousand degree planet passing in front of it, whose atmosphere we detect water and carbon and nitrogen and things. Just to be able to do that is extraordinary. The fact that we're doing it, so we're talking about a little speck of stuff that this telescope saw the change in. So they're going to publish a paper analyzing what these spikes are. Now, could this planet have life? Well, the problem is it's in the multi-thousand degrees. I mean, this would be the point where iron, if it's on the surface, is molten, right? This is a blast furnace thing.
Oh, so they're monsters.
Yeah.
If they live there, they're absolute monsters.
But this was a proof of concept, right?
Yeah.
To say, does this spectrum work, right? Now, how was this done? Because if you saw, you see star, right? Well, one of the clever things with this telescope is has a grid with little tiny shutters, about 100,000 shutters, these little micro electronic shutters that they can open up a little hole. So the starlight's coming there, but they want to look at this one spot, so they find the little shutter, little flap, and open up that hole. So everything else is blocked, but that spot goes into the spectrograph, and they get this rich detail. So they can zero, even though you see incredible detail, right, with those other pictures, they're zeroing down into just a really, really tiny spot and say, I just want the light from that spot. There's no atmosphere to spread it around. We're looking at a tiny spot of a planet in front of a star, and we're looking at its composition. Also, by the way, you can tell the wind velocity because these are not solid spikes. They're kind of spread out. The reason why they're spread out is there's massive winds things going around this planet. So we're seeing Doppler shifts of stuff kind of spread out, which is going to make a little bit complication because not those really tiny, wasn't those nice spikes we saw with those other things. This is kind of, they're spread out a bit because the winds are whipping around on this poor planet.
The lava monster planet.
Yeah. Yeah. So based on our last conversation when we spoke about Mars and how it's just not feasible for us to terraform it because of the thinness of the atmosphere.
Yeah, it's we've got more practical things to do, like getting out of the Earth before the sun goes poof.
Yeah, but if you look at all of the information that's available, is there theoretically possible life on these planets that we've seen based on the calculations?
I mean, this one here, because it's so high temperature, the chemistry is not going to be very interesting. we'll get the notion of what it could have been if this planet was far away from the star and not so blazing hot.
No, but is the atmosphere thick enough to retain water?
Yes, and this is yes, and actually I mean, some of those planets, yes, and so we know where they are. And one of the things that we'll do with the Webb is we'll wait until the planet is out here, and we'll zero in on that spot and say, okay, this is it's because it's going to be a planet far away from the stars, so it's not so hot. And we'll be able to capture it at that spot, open up the shuttle, look at this, peek in the thing, and stare at it to see what kind of chemicals are going on in your atmosphere, which isn't so.
Okay, this is a Bin Podcast exclusive. Elon, if you're listening, we've just fixed it all. So give us your monies, and we'll save humanity.
So this next one here is a galaxy cluster, and even though now there's a cluster of galaxies. It's kind of white spots here. Our clusters are the galaxy cluster, right? Everybody says in quintet of 4 gravitationally bound stuff with a fifth one in the middle. This is a cluster of galaxies. These little white spots here are galaxies. Again, these are galaxies that have 100 billion stars in it. A pile of them piled together, and the distance of this cluster is around 4.24 billion light years. So we're at a stage where the universe was maybe about 20%, 25% younger than it was, and something very odd is happening here. Do you see these? Do you see these little arcs? See these sort of arc, right?
Yeah.
It kind of looks like a galaxy. Well, these are galaxies that are behind this cluster. This cluster has the cluster of galaxies here have gravitational mass, and the light's being bent, and it acts like a funhouse mirror where the light behind it is being bent around it and creating what's called Einstein Arcs. Right? So these things are centered around that. When you see a streak like this, the galaxy is probably behind here, but way behind in the line, and it's being brought out on both sides.
Yeah.
So all these arcs here are arcs. So if we look at something like this is, by the way, is we're talking about something deep into this area here, right? And if we look at this spot here, we can see these 2 arcs. And we turn out this is the same galaxy. So the galaxy is probably somewhere over here, but this galaxy has lensed the light and bent it around, and we're seeing a funhouse mirror of the thing here and here. It's the same galaxy. In fact, we can tell, we can see hydrogen and oxygen in that galaxy that's much farther away. And we tell it's the same galaxy because of the relative abundance there, but it's redshifted. See this peak of hydrogen just a little bit different than this one. This is just a little bit different than this one. They're not identical. The distance of the galaxy, one's kind of going one way, one's kind of coming under, right? The paths are different. So we're seeing the same galaxy at 2 different times. This is slightly different than this. So we're seeing a transition of this galaxy. We see the same galaxy with 2 different snapshots in time being lensed from this set.
What?
Right? Because the path, right? One might be coming under, but another one might be bent way around. So the path of the one that comes in close to the one goes way around takes light longer to travel, which means this is a different time than this one. Same galaxy, 2 different times, just in one set.
My brain just broke.
There are in this cluster. There are a number of galaxies there. We think there's about 48 galaxies we've seen that are lensed. So these are little arcs here. All these little arcs, we found at least 48 galaxies being lensed. These are galaxies, the main galaxy, the main cluster in front is 4.2 billion light years away. These are galaxies much farther back. Now, what do you mean by back? I mean, we talk about redshift, and really, it's a matter of everything like the motion and the expansion of the universe. When we talk about a redshift of 10, we mean that light has been stretched 10 times its original wavelengths. So it might have been nice, glowy yellow, but because the universe is expanded and various other factors, that light wave has been stretched to 10 times its original frequency. This is why you need the Webb. The Hubble can't see down in those frequencies because of the glow in the Earth, right? You need something out in the Webb where you can see those sort of things because the normal starlight here has been so redshifted it's now down in that mid-infrared. And so when we talk about a redshift of 10, we're talking about when the universe was sort of effectively a tenth of its size, when the universe was only 500 million years old. 11, 420 million, 12, 370 million years since the Big Bang event. Wow. So I mentioned that because when we talk about this thing here, look at this set here. It's pretty to see those arcs, right? Those arcs are kind of pretty, but what really is exciting is these guys here, these red spots here, these little dark red spots that don't look like much. But these little spots here, these very what we think of, those are galaxies, and those galaxies are some of the farthest galaxies I've ever seen. This one is 11.3 billion years. This one down here is a record holder. This is the farthest object we've ever seen. The light from that star or that galaxy left there 13.1 billion years ago. When the universe was only about a few hundred million years old. And not only do we see you say, well, okay, there's a smudge. What can you tell from a smudge? Well, remember, we were looking at the spectral stuff. We can look at the spectrum of that galaxy. So there's the galaxy. We look at the spectrum and look at all the stuff and look at its composition to see, does a 13.1 billion year galaxy look like a 11.4 billion year? This thing has had 2 billion years worth of extra stuff to do.
I have another stupid layman question.
Yeah.
Right. So in my job, I have to use a laser measure that has it's got a length. You can't go to more than a certain length because of the light that is projected. Now, how do we know that these galaxies, these stars are that old based on the fact that there's only a certain amount of light that can go before it gets filtered into oblivion?
Yes, and so we can look at frequency, because how do we know this is? Well, we can look at the frequencies, the relative frequencies, because you want more than one spike. So say, well, there's the hydrogen combination for this one here. That we see the same. Do you see the same chord but transposed? And that's because it's been redshifted even more. The same chord now we see just those two top notes with a third one off the chart.
Right.
And that's where it's getting redder and redder and redder. Where this one is even the James Webb can barely get to the bottom base note that was been transposed down, where the redshift has gone way out, in terms of stuff. So where it's been transposed more than 12 times, that the light frequency's been stretched 12 factor of 12.
So is there a possibility that there are stars that have been on a smaller scale that have extinguished that we will never see because of their mass and the fact that they went out a long time ago? So
because certainly the thing is that this galaxy has done a lot of stuff in the last 13 billion years. It probably merged with some other galaxy and it's probably part of some other thing that's got and in fact, those stars, many of the, if there's any sun-like stars in that galaxy, they've long since gone.
Yeah.
So some of the low mass red dwarfs might still be around, but this galaxy has probably been absorbed by some other galaxy. It's probably merged into something. We can look at this galaxy again. The light left 13.1 billion years ago, when the universe was only a few 100 million years old.
Yeah. So we're constantly dealing with looking back at, a bit like there used to be a show over here called Time Team, hosted by Tony. What was his name? He used to be in Blackadder. I forgot his bloody name. But yeah. So no, not Ryan Atkins. Tony.
I know what you're saying. The Blackadder is, yeah.
Yeah. But basically, they used to go to all these different sites over here, and they dug down, and you keep digging down, and you find all these new, like Neolithical sites and all that kind of stuff, because you had to go backwards to find out what was going on before.
Yes.
And it seems to be the same with anything to do with the stars, because we are only getting a light that started, as you say, millions and millions of years ago. So we can only determine what's going on back in the past, but that thing doesn't actually exist anymore.
So with this galaxy here, the universe was only 370 million years old, right?
Only.
Our Milky Way hadn't been even formed yet. We were probably some dark blob someplace that hadn't, and yet we know this galaxy has some stuff going on because we can see neon.
Tony Robinson, that was his fucking name.
Yes, that's right. Interesting guy. Anyway, so we can see neon. How do we know it's neon? Because we can know the relative. We know the chord. We know the musical note of where oxygen, the violins and the cellos and the bass and so we know the music being played, and we can see, yes, these are neon spikes. Now, what do you mean by seeing neon? Well, we're seeing neon in a galaxy. How do you get neon? Well, one of the best ways is when you have a star that goes boom. Star that goes nova. Remember we saw that previous thing of the nebula? Well, to get neon, I mean, the early universe, just after the Big Bang Flash, had about 70% hydrogen, maybe 24% helium, and then 1% lithium. That was it. To get neon, to get more complex elements, you need to have stars that were born and died. So we're seeing, now probably those are massive stars that came on in there that already went pop and had their supernovas and scattered. So we're seeing stars that have captured neon from a previous death of a star, which kind of is puzzling because you'd think if the universe was only 370 million years old at the time light left here, there wouldn't be the time we thought, well, it takes a while for a galaxy to form and so forth, and we might not, the first billion or 2 years you won't see galaxies. Well, no, it turns out galaxies are formed very early. Because one of the mysteries we don't quite understand is this chicken and egg problem, right? Was it that a bunch of stars formed?
It was chicken. It was chicken.
100%. Do you get a bunch of stars forming in a cluster and they kind of came together and made a galaxy? Or do you get a bunch of gas that collapsed and created stars having to get together, or some combination of the two? What came first, the star, the galaxy, or some probably more complex answer to it? So the fact that we can see a galaxy when the universe was very young, and we can look at what's in there and look at its chemical composition, and we can see what the universe was like back in what we call the Dark Ages. Because after the Big Bang Flash, there wasn't much creating light until the first stars formed. One of the goals of the James Webb Telescope is to see some of the first stars that ever switched on after the Big Bang. And And this was a exposure that took around 12 and a half hours. So that big thing you saw the president announce, this image of the deep field. This is only 12 and a half hour exposure. Because they wanted to, and the Hubble, if the Hubble wanted to get this faint, let alone the fact they couldn't see the red stuff, right? It would have taken the Hubble around 4 to 5 weeks just to get something that faint, right? This thing got put in 12 hours.
Landon, let's just take that image. Go back to that previous
this one
image.
here. Yeah.
All right. Just look at the beauty of that. It's a random assortment of colors and shapes, and a black background, but it's just so.
And you look down there, you can see
beautiful. It's just
these fuzzes here you see are galaxies far, far, far behind. Galaxies, right? This one here, it's kind of fun, funhouse shaped distortion, is a fairly evolved complex galaxy. It is mirror warped. Look at this spiral here, right? We just thought it was a star. No, this is a spiral galaxy. See the spiral arms of this thing, right? Look at the stuff over and these spiral galaxies. These bright stuff here are stars, kind of in front. But you can see.
Just look at the shapes. You have completely symmetrical shapes mixed in with completely random shapes that are forming in that exposure time.
And you might say, well,
that one there on the top right, that's kind of like a little wisp, going off in its own little thing.
But this is probably like a Stephan's quintet. There actually are several galaxies in here. You see the galaxy cores, and remember the Stephan's quintet where everything's kind of stretched and so forth. So this is not gravitational lens. These is a bunch of galaxies that have done this dance and whipped around and are stretching each other and pulling it on each other. Versus here, you just see a pair. You see a Milky Way-like galaxy, a little companion Magellanic Cloud galaxy on the side, satellite stuff.
Yeah.
And again, the details behind here. This is only for 12 and a half hours. This telescope wasn't really trying. When we steered down the spot for
look at that shaft to the right.
Yeah. So you see the diffraction spikes from the effector thing. So this is right, but again, we see. So one of the things they're going to be doing, people analyzing this stuff, is they're saying, okay, where do we see the multiple galaxies, right? Because we know that these two are the same galaxy, just from different paths. So now we can see the same galaxy in 2 moments, at 2 distances, right? We can see what the galaxy was like at two times. We see it now, but light left different times, the same thing in spots, right? And we can see even fainter, a lot of these Einsteinian arcs. These are galaxies way behind it that we're just now seeing, these little faint sticks of stuff. Plus, well-developed galaxies. So we want to know what was the universe like early on, and this is giving us this sort of thing. And we're going to look at the chemical compositions, the elements coming from some of these early galaxies when the universe was quite young. So
we need to do a part 2 on this, because there is so much in here that we're not going to have time to dissect tonight.
We're near to the last image, but I do want to show you difference between the sort of all spectrum stuff versus just the bottom chord, the bottom octave, where now some of the more fainter stuff comes in.
Also, I love the fact that you're linking this with music, because it's so fucking apt. Because
and we know, because a lot of astronomy is about looking at the chords, the relative frequencies. You want to know, and the relative strength of those frequencies tell you something about the instrument. A violin sounds different than a flute, even though they might be playing the same note because of the harmonics are different. Same thing in the universe.
you can play the same chord in different instruments, but have different resonance.
Yes. So again, you can look at stuff. You can look, and besides just a pretty picture, right? That's nice. You can look at things in different frequencies. So there's lots of data just besides a pretty picture. So final bit here, and what happened? I'm going to get preview to stop what it's doing. Jupiter. Let's go to Jupiter. Come on, Jupiter. Where do we have it? Why? One moment, please, because this is an image here. Okay, I'm going to quit thing here.
The Cartwheelian Empire has launched their first assault. A cyber attack on Landon's computer. We've got too close to the truth.
Fucking David Icke attacked his computer.
They've come for us. I imagine the Cartwheelians are Klingon.
So I'm going to show you the last thing, and this is something that just came about from the set. If I can get it back to the spot here.
Look at that tiny continent. Look at that teeny tiny continent.
Yeah.
That's a country. That's Africa.
Oh yeah, it's just one thing, isn't it?
Yeah.
Everyone's the same.
I'm trying to recover the set here. Something is blocked on the set.
From Tunisia to South Africa.
Yeah, this is that black spot there in the center of Africa. I was under that spot. That was a total solar eclipse. I was in Libya, in North Africa at the time, and so this is a satellite looking down on top of it. And what I don't see happening here. I have it back.
That's not Libya, is it? I thought Libya was like on the north.
Libya's up around here, right? So the moon shadow is heading this way, and we're sitting right here. So there's Libya's North Africa here. There's Egypt. There's Algeria, Morocco.
Yeah, I thought Libya was
more
northern.
I'm actually right there where the cursor is.
Okay.
So the final thing I wanted to show you here, is a new image set that just came out.
Landon, I just need to interrupt. Mikey, he thinks it's round.
Let him have his fun, Wayne.
Okay.
he's think he's got it all figured out.
So this is the planet Jupiter, and one of the things where the Hubble, the Webb telescope was slewing between two objects, and someone realized, it's going to go past Jupiter, so they just deviated just a little bit to go and say, let's take a snapshot of Jupiter. So as it's going forward, we're seeing Jupiter. You can see the red spot.
Yeah.
Mm-hmm.
Again, we're talking about something that is that's 2.12 microns. So it is going to be some 5.5 octaves below visible light. So the Jupiter, you're seeing the heat from Jupiter, and you can tell this equatorial band is actually much hotter, but also the storm of the red spot is also hot, right? There's a lot of energy going on there.
Yeah.
Now you see this dot here. Well, what you have is the moon Europa casting a shadow onto Jupiter.
And it's cold.
Yes.
Yeah.
It's dark there. Now they say, well, while they're there, again, this is a short exposure because it's got going between this spot and that spot for people who want to do it. While it was going on, they said, well, okay, let's look at it. Let's look at it at the bottom layers. Let's look at it all 7 octaves away, right? Now Jupiter has a temperature. So Jupiter at those wavelengths, again, we're talking about within our solar system, those wavelengths is actually quite hot. I mean, the normal temperature for things that are 3.23 microns is Jupiter's hot and glowing compared to that temperature. So that's why Jupiter almost got overexposed. And we can see the moon here, Europa. We also see another moon. I believe this is Thebe, and Metis is another moon over here. So we see two other moons that weren't quite apparent there, but we can see because of the heat the moon's giving off. But
Oh wow! Yeah, I see that now. Yeah.
Do you see this? Do you see
Yeah.
that little thing? This is the ring around Jupiter. Jupiter has rings. We saw those rings when Voyager spacecraft was going by, and big nice telescope going by, looking off the side, and we saw.
I think you'll find that's Vija.
But
Star
we
Trek,
see
the motion picture.
We see that the Webb telescope is good enough. We can see the heat of that very, it's not a big ring like Saturn, right? Saturn's got the nice massive ring. This is very, very thin, wispy. This is not Saturn. This is Jupiter. And Jupiter has a very, very tenuous ring that we only saw by a spacecraft near Jupiter, looking off to the side, not being blinded by the glare of stuff. But we can see the heat of the ice crystals orbiting Jupiter in this little, very, very thin Gossamer ring. And so we're able to go back and look, because you can see this ring has got lumps in it. So here's the ring on this side, and this is the ring on this side.
What? You may not know this, but why does Saturn's rings only appear in a kind of hemispheric way? Why are they not just kind of
all around? Well, the rings are going around Saturn's equator.
Mm-hmm.
Right? If what happens is that the rings, you've got a bunch of gas, so there's debates about how they're formed. But let's say you had some planet that got shredded, and you have torn in pieces, and you got this. So the planet was kind of going around Saturn, but now the gravity of the various particles of that shredded moon pull into each other, right? So even though you're whipping around, so they're being stretched out with centrifugal force, the gravitational part of the rings wants to collapse it down, right? The force of the particle itself wants to smush down, but they're being slung around Jupiter or Saturn. So they're being pulled out, but they're being pulled down in. So instead of having a ball where everything goes their way, it tends to start flattening itself, and that's in fact this is what happens. This is how. But
the thing is, you do have satellites that will rotate in that way.
Oh yeah,
so
it's not exclusive.
It's weird. It's weird that they've kind of compressed into this hemispheric ring.
But it tends to be because of the orbital motion, the spin, and the collapse, that they tend to go into a plane. It's the same, because it probably started off all higgledy-piggledy all over the place.
Yeah.
One of the things that kind of come in right angles, if they're going the opposite direction, they smash into each other and stop, right?
Theoretically, all of the GPS satellites that are up in our lower orbit, surely they would kind of find an equilibrium, which would mean they would go to that hemispheric kind of satellite position.
And imagine you're making pizza. So you got that dough, and you're doing kind of the dance, and you're spreading the dough around. The doughs want to go and stretch out thin and collapse. It doesn't stay a ball. It tends to flatten out. And this is the orbital dynamics. And the nice thing about this is that we saw those planetary nebula being formed in the Karina Nebula. Those are those lumps of spinning dough that are spinning around that will collapse into some plane. The stuff that's going counterclockwise rounds each other, so that the majority of stuff say we're going to go this way, you don't go that way. The stuff that's going around, is either thin or runs and stuff and collides and so forth. So you end up getting a dominant direction and gravitational attraction together to form the general plane. So this ring around Jupiter is around its equator, which is where the major planets of Jupiter go. Same thing with Saturn. Yeah, it has oddballs going around, but those are tiny rocks way out there that haven't.
I apologize for my simplistic question.
It's a really important question, and it's one of the things that we want to be able to see these new planetary systems. Again, I'm I'm a planetary scientist. I get excited about planets, and to see
Well, mate,
processes being
there's
formed.
there's websites for that. All right, we don't do that here on the BIM podcast. All right.
I apologize. You keep it a family show, but we see these nebula, these planetary systems.
Yeah, we see these nebulas. Yeah, all right, of course.
We call protoplanetary disks. And Jupiter has its things too. So we think these rings don't last a long time. Something happened with Saturn where some moon got really shredded and put a lot of material. Eventually, we think that the rings will rain down in on Saturn and it'll drift away. But Jupiter's got these big moons around it that kind of make it hard for rings to keep forming. But the fact that this thing going by and said, oh, let's just look at Jupiter. Wow, we can see something which only spacecraft next to Jupiter could see. And see it in detail is extraordinary. That's the power of the web.
So I'm wondering, did that not heat up the telescope?
Well, I mean, yes, the photons that bounce off the mirror hit a detector, and the detector said energy, right? That's what a detector does.
Yeah.
Now, it's not bright like the sun, where it would then cook the telescope. It's a very, very thin. So it's no more than someone's film or some light bulb across town is going to heat you up. Yes, technically you're getting energy from it, but I wouldn't count on keeping you warm.
Well, I know this thing has to be like 1 billion trillion degrees below everything. So it's like, man, don't look at that. That's too bright for you. You blind yourself.
But you can tell from its lowest notes, its base notes, that Jupiter's blazing hot. It looks like a star, right? Because relative to the telescope, Jupiter's hot. Now, and level of pixels there, but the fact that you can see details, you can see the moons. The moons are even overexposed. You can tell the Europa. You can see the disk of it's got enough resolution details. We can see the disk of the moon orbiting Jupiter.
Mikey, I've got to say, I find Landon's testimony implausible. The Earth is flat and winter is coming. That's it.
Yeah. So there's a moon here, stuff that got blown out, pixels blown out. A moon here you can see, but it's bright enough you can see the shape of the moon and diffraction spikes. The moon back here, but again, that ring, we're able to watch the ring go by, and so it's one of those things where when they're pointing the web around, and they're going from A to B, they're able to say, well, along the way, why don't we just look at this, right? So while it's slewing, they're watching stuff drift by. So this was like a slew and happened to be near Jupiter. So the life of the Webb telescope is very busy, and even when it's just slewing from one spot to another, it's taking data, and people will, the science, the missions for this year have already been assigned. The people, astronomers assigned time, have got their stuff to study, and even the transitioning from moving from this part of the sky to that part of the sky, they have other missions to say, look at this along the way. There's also some spare time. So if there was an emergency that happened, like we find a comet, interesting comet, there, we can, there's unallocated time to say, go, let's look at this comet. Or if a star explodes, we can go and look at those. So they have what's called discretionary time if there's an emergency for that. But right now they're taking applications for the next year, the next science year. Now that again, the Webb is working slightly better than what they had hoped it would do. Yeah. The fact that it worked is amazing. And that it's working at tip-top performance, and it's delivering data so rich. Again, more than pretty pictures, it's these spectra of stuff that tell us about a galaxy that was formed just when the universe was just a baby, and seeing sterile evolution in the process is just extraordinary. And then to take something like a planet on a nearby star that's a thousand, that's around 11,000 trillion kilometers away, and looking at water vapor in its atmosphere and other chemicals is just extraordinary. So we're going to get lots of data coming through.
Can we even have water vapor at those temperatures? Like, what would that even just be, like a steam, right?
Yeah,
just like
it's steam. It's a steam bath.
Yeah.
But again, it is going to tell us something about what this planet is, right? We're going to look at some of those signatures now. When you deal with a planet that's not so high temperature, far away from the star, there's some that we know that kind of move far away that we know which side the star is going to be on. So we can open up those shutters and peek at that one spot to see, can we get some chemical compositions. There's another thing that's going to happen called star shade, where let's say we find a planet and the spectral wiggle signature says there's water vapor, there's carbon, there's carbon compounds, there's carbon chains, there's nitrogen, there's magnesium and all the good stuff, and it's not a boiling hellhole, it's not a frozen landscape, it's in that Goldilocks zone. The next thing they do is they have a program where they take a little tiny spacecraft that's got this umbrella-based thing, and they fly it in front of that star about 1 million or so million kilometers away from the Webb. The Webb has to be looking at the star, and the star is, and we'll be looking like something. So maybe the Webb is looking at this star here, right? And it sort of says bright, 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 bright. Even with the Webb, it's kind of hard to look down in that star and see what's happening. But you have a little spacecraft have this orbit where it just goes in front, and it for a moment in time, some minutes to hours, it blocks the light of the star, and we can see around the side. We can see around the side, and at that point, all of a sudden, you might see planets in a thing and stuff happening, right? And what they'll do is they'll open up those little shutters where the planets are, and they'll get the spectrum to see, is there interesting chemistry going there? What's going on for the planets around that nearby star?
What's the most promising thing we could find in another planet's atmosphere? Like, what is bar none?
A pub.
What is bar none aside from the pub?
Yes.
Pubs floating in the atmosphere.
Okay, so
sounds dangerous. The rainfall is murderous.
I mean, the way the physics works, carbon is a really good atom to build chains of stuff, right? Mm-hmm. So the reason why organic chemistry has all those carbon things and rings and so forth, because carbon has all kinds of ways to mix and match each other, right? Much more creative. So you can the compounds you can build with carbon are extraordinary. And the chain you can build, the polymer chains you can build with carbon are quite, it's just the way the physics works. And again, physics here is the same physics out there. So if they have carbon out there, their carbon can link up to stuff. But you need more than carbon. You need some phosphorus. You need some magnesium. You need some nitrogen. You need some other stuff. And you might some iron to have it. So what we want to look for is rich chemicals. So let's go out on a limb. Let's say we want to see whether a planet has plant-like material and chlorophyll stuff on its surface, right? Things that can convert sunlight into energy,
right,
on its surface. Well, we know what chlorophyll looks like or chlorophyll-like compounds look like in the lab. We'll then look at those relative signatures and say, do we see the musical notes for organic compounds? Not just methane, not just cyanide or something like that, but some more benzene rings and methane, right? Got methane. Well, why is methane? Well, on Earth, one of the ways that methane gets in, things farting, right? So we might be able to see fart gas in the atmosphere of stuff where the atmosphere might be thick, but things are farting and the fart gas gets trapped in the atmosphere. You say, well, something down there is generating methane, and not only methane, but it's also got these long carbon compounds. Maybe it's got silicon chains of stuff and other things like that. We're looking for interesting chemistry, not just elemental hydrogen and neon. You need that to get to the planetary stage. But once you're at planetary stage, you need time to do some interesting chemistry. So
I mean,
so
like, is there anything that is there something that if we saw it, it could only be intelligent life? Like if we saw like, I'm trying to think of an element, you know, but if we saw like neon,
hydrogen.
Well, okay, so intelligent stuff,
something that's clearly from like manufacturing, or you know what I mean, like exhaust.
You want to see long complex molecules of whatever elements they're in that are complex enough that they can mix to do imperfect replication. That's part of the difference between just sodium and chlorine get together and forming salt. Nice, but not spectacular. Versus a long compound molecule that can replicate itself imperfectly and evolve, right? Now, whether or not there's intelligence is harder to tell, but at least you know, the first thing we'll say is, do we have the seeds for interesting chemistry? The second thing is, are the conditions right? Because that planet we saw, it's got water and other things there, it's so high temperature, it's hard for chemistry to stay to do anything interesting. The other side of the coin is a planet that's way out there in cold space where it's all frozen and it might have been, but it's not warm enough. You want to find things where you might have liquid water, which is a great solvent. Yeah. Or you might have some silicon-based chains that do some interesting stuff. You want to see the chemistry of those complex molecules and see whether or not they're potentially are doing or evolving stuff. Now, if you saw a planet in Goldilocks zone, wasn't too hot, wasn't too cold, it's got interesting complex chemistry going on, maybe different than ours, but still it's got chemistry going on. That's where you can then focus on and do more detailed stuff to say, okay, let's pay attention to that spot. So some of the nearby stars that we've discovered planets, what are the nature of those planets? Are they just a rock or to have an atmosphere with stuff going on there? Well, we'll be able to tell that with the Webb more than just pretty pictures. Most of what astronomers do is deal with these wiggly lines. That's what if you go to an American Astronomical Society thing, you'll be looking at charts of graphs like that where people will be saying, well, this dip, right? Something absorbed light at this frequency. Relative to what? Well, relative to hydrogen. There's something that absorbs it. So there's some material that absorbs light where you had a dip down there.
Ring.
What might that be, right? So people start to so we have these graphs and start to zero in and stuff. I mean, pictures are nice. And
Landon,
this is physics.
Landon, I'm sorry to cut you off, but I really need to do one. It is 20 to 11 over here.
We have finished the thing. We're finished. I just say, any other questions that people have?
No, it's been an absolute education.
They're all stun locked.
It is. There's a little bit of science stuff. We'll get more stuff coming out.
But what I'm going to do is I'm going to try and see if I can queue you up with Professor Howe and let you two just talk, and we'll just sit back and just sit there and nerd out.
He wanted to have a physicist fight, and I said that's not Landon's style. He doesn't use bladed weapons.
Professor Howe will come with his own homemade lightsaber, and you can come with your batleth. It's fine.
Yeah, it'll be a fun thing to do. By the way, I will point out that dip there, we kind of see it over here too. So Yeah, there's some interesting, but stuff has evolved. So anyway, that's you go to a astronomy conference. They might start off with a ice cutter slide like that, but they quickly go past the pictures to the data, where we'll do two things. We will uncover information about the early universe, or the early formation, or the existence of planets around nearby stars. But the other thing is we're gonna come up with a bunch of questions where we go, huh? Right. That's the next thing is when we understand, we don't understand, right? When we look at this galaxy and you say, well, we think blah blah blah, and the galaxy says, here's something unusual, explain this, right? That we get most excited when we know we don't understand, because then we can learn, and it's so fun, and then it's just getting started. So thank you very much for
No, thank you, because the best and most humblest thing you can ever say is I don't know, and then when people like yourself come along, educate us, and we can go, yeah, do you know what? I didn't know that.
Yeah.
It's the beauty of education. Just saying, I don't know.
Yeah. So we'll find out what we don't know, and then we'll work on learning something. So
yes,
let's meet again for we get some. Let's wait for some of the papers to come out. Some more of the image stuff coming out. There'll be less press releases of pretty pictures and more papers on why, which is really reason why the web exists what it is. But I must say, I want to thank the many tens of thousands of engineers who were so careful. There were hundreds of ways this thing could have gone wrong, and I'm not exaggerating. Where any one thing would have just doomed the thing and said, yeah, well, we tried, right? And it works, and it's working spectacularly well, and we're getting good data, and we're getting very confused. I talked to a gentleman who was telling about the Jupiter stuff, and it's like, you work on stuff. He says, boy, we're trying to write this paper, and we are so confused. It'll be a fun paper. So, like, ooh, no, gotta wait till the paper posts. So all the stuff will come out, and eventually the rule is everyone can see the data, but the people whose time it is, they get the first right to publish. And then when they publish the data, and we get to see the data and check to see, yes, no, you forgot this thing. Because that's the problem, is that they might have been focused on this spot, and someone says, but did you notice what this thing is doing over here, right? So we're waiting until they publish, and then they go say, yeah, but look here. So thank you again.
Yes, we will have to have you back when we get more, when the papers finally come out. So for Jartin, Brenna, Wayne, and me, Mikey Famine, thank you, Landon, and thank you guys for watching. We will see you guys on Tuesday for the hot tag. Bye.
Goodbye, everybody.
Bye.